something else that from time to time may be helpful to do is what is called a projection. What that means is I'm going to take, so I've got this vector A, and then I've got another vector B, and we can move it around wherever we want to. Let's make it a little bit smaller so make it more obvious. And so what I'm going to do is I'm going to project, I can do it either way, but I'm going to project B onto, projection of B onto A. And so what that amounts to show it in a kind of diagram here, I'm going to take that tip end of B and bring it down in a perpendicular way there onto A. And so yeah, this is the projection of B onto A. And the way we write that, projection of B onto A. I'll forego the vectors there, but yeah, so that vector there, it's a vector. It's called the projection of B onto A. So A is this whole thing. Projection of B onto A is just that little piece right there. So it's kind of a shadow, one way I've seen it described. So you're kind of thinking about it, what the shadow, I guess at high noon or whatever. All right. Well, here's what we got. If you look at one way you could look at this, that sets up a right triangle, and so this angle right here, which is theta, right, the angle between them. So the cosine of theta would be that magnitude of that projection of B onto A, divided by the magnitude of B, because we're talking about the magnitudes there. And so multiply both sides by the magnitude of B, get the magnitude of the projection of A onto B onto A, is magnitude of B times the cosine of theta. Okay? Now, that's, again, okay, but we could get a little better formula if we look at this. Let's think about this, all right? So again, A dot B, I mean, we still got the dot product there. A dot B would be the magnitude of A times the magnitude of B times the cosine of theta. Well, if you take that and get this equivalent thing over there, this equal thing over there, divide by the magnitude of A here. So A dot B is also equal to magnitude of B times the cosine of theta. Well, if two things are equal to the same thing, then they must be, oh, forgot my magnitude of A. I said it, but didn't write it. So if two things are equal to the same thing, they must be equal to one another. So the magnitude of the projection is, this is a little better formula, or easier to work with for me, because you're just taking the dot product and dividing it by the magnitude of A. Okay, so that's the magnitude of the projection, or the scalar projection of B onto A. right? So that's how long that thing is. All right, now, if we actually want to get the unit vector for the projection of A onto B, well, as we know, we would take, so to get an actual vector out of this, all right, so we've got this. This tells me how long it is. Now I just need the direction, right? I need the direction of this projection. Well, the direction of this projection is the same direction as A, so all I have to do is take the unit vector of A and multiply it by that scalar amount right there, right? Well, the unit vector in the direction of A is, remember, it was just A divided by the magnitude of A. And so if I take that, which gives me the direction A is in, 1 unit long, and multiply by the scalar, then that's going to give me that vector, isn't it? Because that's 1 unit long, multiplied by the scalar, that's going to give me this vector. Make sense? So the projection of B onto A is, you just take that amount, A dot B divided by the magnitude of A, times the unit vector in the direction of A. And the way they usually write that is just regrouping, I guess you might say. Take the magnitude of A, dot product, then the magnitude of A squared, which, that basically get rid of that square root times your vector A. Kind of put the scalar parts together. So that's our vector projection of B onto A. So, yes, a couple more formulas, right? Okay, so that's one of those. Oh, forgot this term. A term they'll give to this, it's called the component of B onto A. Comp. Another name. I guess they want another name. But it's just that scalar projection of magnitude. Okay, so find the scalar and vector projections of B, which is 6,5, onto A, which is 3, -2. Yeah, so the scalar projection is this component B onto A, and it is the dot product divided by the magnitude of A. Easy enough to do, right? 3 times 6 is 18, minus 10. 3 times 6 and 5 times -2, is that right? Magnitude of A, well, you just do the square root of 9 plus 4, so it'll be 13, so you got 8 over the square root of 13. So that's that one. And then the vector projection magnitude, dot product divided by the magnitude of A squared times A. All right, so the dot product, we already got that, that's 8. The square root of 13 is A, magnitude of A. So get the square root of 13 squared times A, which is 3 negative 2. So really you got all parts of it computed, just have to put them together, see what, so it's just 8/13 times that vector. Like I said, that usually just gets rid of that square root, squaring it. So that would be, if we go ahead and put the 8/13 in there, just distribute that. 24/13 would be the I component, and negative 16/13 is the J component. Again, it's just a formula, plug it in, you got it. Is that all right?